5.4 Interpreting the Kelvin-Planck statement. So previously we discussed the Kelvin-Planck statement. It is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surroundings while receiving energy by heat transfer from a single thermal reservoir. So in other words, the thermodynamic cycles must have two thermal reservoirs to produce positive work. The Kelvin-Planck statements can be expressed analytically as follows. So work produced by a thermodynamic cycle with a single reservoir is zero or negative. The system cannot produce work with a single reservoir, so it has to reject some amount of heat to produce a positive work. To show what that means, let's consider a thermodynamic cycle like a heat engine. So let's assume the system has interaction with a single thermal reservoir. So the system is connected to a weight through a pulley. So first consider that work is done on the system. The shaft rotates as the mass is going down, and the system rejects heat to the thermal reservoir or low temperature reservoir. Since heat is rejected, this is called reservoir, and the system maintains a constant temperature. So when the work is done on the system, it is negative according to the sign convention. So when the heat is removed from the system, it is also negative. So both work and heat are negative in the given conditions. So negative Q minus negative W equals 0. So if there are no irreversibilities, Q equals W. So all the work is converted to the heat. So far it looks good. Recall that the cycle indicates that the system returns to its initial state at the end of the processes. Now to complete the cycle, consider the reverse process. Let's say work is done by the system. The shaft rotates in a reverse direction as the mass is going up. So work is positive. To make it happen, heat needs to be transferred to the system from a high temperature source. But with the given conditions, heat cannot be transferred from the low temperature reservoir to the system. So we only have a single thermal reservoir, and it is a cold reservoir. So therefore it is not possible to complete the cycle. It is an irreversible process. So the net work is negative. So consider the heat transfer is a reversible process. So when the temperature difference between the system and the thermal reservoir is infinitesimally small. So we may assume Cauchy equilibrium heat transfer between the system and the thermal reservoir. Then the system produces a positive W, positive work. In that case, Q minus W equals 0. So net Q equals 0. The net W equals 0, as we assume there are no internal irreversibilities. So the analytical form of the Kelvin-Planck statement is W equals 0 for no internal irreversibilities, and W is negative if there are internal irreversibilities.